Okay, so we just introduced the Bellman-Ford algorithm. So there's one more thing I want to say about this algorithm. Okay, so in particular, now in the Bellman-Ford algorithm right now in the code, we run v minus 1 iterations. And again, you have to ask yourself, why do we run v minus 1 iteration? The reason is because that we know that if I run k iteration, then I can only guarantee that all the nodes whose shortest path it has k, at most k edges from the source are their distance are estimated correctly. Okay, in order for me to make sure that all nodes has a correct distance estimate, I have to prepare for the longest possible shortest path, which is v minus 1. Okay, but in practice, if you know that your shortest path will never be more than 5 edges. Okay, if you know that, so if you know that your shortest path, so if I know that the shortest path, we know that any shortest path in my graph has at most, say, m edges. Then I don't have to run we know that clearly m is smaller than v minus 1, okay? But if we know that this m maybe is much smaller than v minus 1, then you don't have to run this outer for loop v minus 1 iteration. You only need to run the m iteration, because after m iteration, we're guaranteed to discover all the nodes whose not discovered, to find the correct distance to all the nodes whose shortest path at most m edges. Okay, so I can in general replace this v minus 1 with m. Okay, so if we have, but since we don't know what is m for a general graph, that's why we run v minus 1 iteration to guarantee that we don't miss any nodes. Okay, but there's another way, even if you don't know what is m, there's another way that help you to detect that. Okay, so after every round, okay, you can ask yourself, in this round, did I find so every round means that you're performing this update all edges operation. Okay, so if you update all edges, but throughout the entire update, nobody found no edges discover new paths for you. What does that mean? That means that even if you now keep updating again, no one is going to change. Okay, that means that to all the nodes, the update is no longer improving. You already found the correct shortest path distance to all of them. Okay, in this case, you can stop early. You can terminate the algorithm early. Okay, so this is the so-called early stopping idea of the Bellman-Ford. So I don't have to run v minus 1 round. What I can do is that I can have a flag to track. At the beginning, this flag is false. If any updates happen, then the flag become true. Okay, and if in the end my flag is still false, so that means my flag means that there's no change. Okay, then that means that we are done. Running more updates will not be able to find any other paths, because I already went through all the edges and none of them discover any new paths for me. So if you repeat, it's just going to be the same. Okay, so then we break it and then we just return early. So this is you can in practice, if your longest and shortest path is not very long, then this early stopping trick will help to make the algorithm run faster, namely stop earlier. Okay, of course, the asymptotic running time, unfortunately, is still the same as before. It's still v times e, because in the worst case, I may still have to run v minus 1 rounds. Okay, so that's why asymptotic doesn't change, but in practice, it often would return early, especially for simpler graphs. Okay, all right. So that's one thing that I want to talk about for the Bellman-Ford algorithm. So this is a modified Bellman-Ford algorithm with the early stopping version. Okay, all right. The second thing I want to say is about the negative cycle. Now, earlier we said that if your graph has negative cycles, then the shortest path is not well defined. Okay, and we have assumed that when we define shortest path, your graph doesn't have negative cycle. But what if your input graph has negative cycle? Okay, and nobody tells you that. How do you know? Okay, it turned out that Bellman-Ford algorithm can also be used. If that is the case, the Bellman-Ford algorithm can actually detect it. It actually knows that, okay, something's wrong. Your graph must have a negative cycle, in which case we're going to return saying that the graph has negative cycle. So how do we detect that? Well, remember that if I have a negative cycle, like in this case, oops, it should be -2, sorry. Okay, this should be -2, okay? So this is a negative cycle because if I go around here, the length of the cycle is 2 plus 1 minus 3 minus 2, which is -2. Okay, so this is a negative cycle. Okay, now recall what's the issue with the negative cycle. The issue is that if I have a negative cycle, I can just keep decreasing my path length. Okay, so I can keep circling around the negative cycle, and then the distance will be distance of a path going from U1 to U6. If I just go around this many times, just keep decreasing. There's no end. You can go do this infinite number of times. Okay, and now we know that if the graph does not have any negative cycle, okay, then the estimated distance has to stop changing after v-1 iteration. Why? As we already said, that's the correctness of Bellman-Ford algorithm, because after v-1 iteration, we already found the correct estimate distance to all nodes, because any shortest path can have at most v-1 edges in it. Okay, so after v-1 iteration, we found all shortest paths, and the estimate will not change anymore. Okay, you can perform more updates operation that doesn't change the estimate. You cannot decrease anymore. Okay, but if the graph has negative cycle, it turns out that because of the existence of the negative cycle, again this should be -2. Okay, because of the existence of negative cycle, now if you can after v-1 after v iteration, if you continue to update all edges, the distance just keep going down, just intuitively, just because that you always can find a longer path going through the cycle, which has a smaller and smaller distance. Okay, so the way that you detect a negative cycle is that you basically, so Bellman-Ford can be modified to detect negative cycle. You run, instead of v-1, you now run v. Oops. So you now run v instead of v-1 rounds. Okay, so you run v rounds. Okay, now if the graph doesn't have negative cycle, for the last round, the vth round you're performing or update all edges, no distance, no estimate distance can change. Okay, but if an estimate distance is still decreasing in the vth round, then there must exist a negative cycle. So I'm not going to prove this formally, but intuitively, that's because that you can always just circle around those negative cycle and it gets the length shorter and shorter. Okay, so from algorithm point of view, it's very easy to add. So this is the final modified Bellman-Ford algorithm with both early stopping and also negative cycle detection. Okay, so early stopping is that I basically track after each round of update all edges, I see whether there's any changes or not. Okay, if there's no change, that means we're already done. We already found shortest path distance estimate for everyone correctly, so we simply return. Okay, otherwise, if after v iteration, we still didn't return from here, that means that there must be a negative cycle. Then we simply return that contains negative cycle. This becomes true. Okay, or you can also print. You can print a message saying that there exists the input graph has negative cycle error. Okay, because the shortest path is not well defined in this case. Okay, that's it. Time complexity. This just change the number of iterations from v-1 to v in worst case, so it doesn't change the asymptotic time complexity of this algorithm. The asymptotic time complexity remains v times v. Okay, and that's all for today. And next time we're going to talk about a more efficient algorithm called Dijkstra. But the price to pay is that the Dijkstra cannot handle negative weights. The input graph or the edges has to have positive weights. Okay, and that's all for today.